We're continuing now in Chapter 6. This video details another method for analyzing trusses, and this method is called the method of sections. So it again uses the idea that if a truss is in equilibrium, then any part of the truss is also in equilibrium. So what we want to do is cut the truss along an imaginary line, and then we'll consider what were previously internal forces to be external forces. The figure here shows a truss, and say we want to find the forces in members BC, CG, and FG. The way we would use the method of sections is to draw a line through those members, as long as it's no more than 3 members, and we will divide the truss into 2 sections, and then we'll treat each section as a rigid body. So here we are looking at the section on the left. We really only need to work with one of the sections after we cut it, because that one that one rigid body will give us the erstwhile internal forces as external forces. So here we had the free body diagram for the section that we made on the truss, and you see the external 1,000 Newton force is shown, and then we have the forces in the members, the ones that we want to find out, and they're shown as external forces. And so that's what the method of sections does. It allows us to treat internal forces as external forces. So for this rigid body, we will apply the equations of equilibrium. So we have 3 unknown forces and we have 3 equations. So once we have the free body diagram, we can solve for the unknown member forces, just like in previous problems whenever we solved for unknown external forces. So in summary, we will make a cut based on the desired forces, the members that we want to analyze. And it's possible that we might need to get the support reactions, like say, or it might be easier if we go ahead and get the support reactions, like in some cases anyway. A truss could be supported on both ends, and so you'd have to get the support reactions at one of the ends. We'll see examples of that later. So anyway, if we do want to get the support reactions, then we would solve for those before making a cut. So we would analyze the truss as a whole as a rigid body, get the support reactions, and then go ahead and make our cut and just look at one section of the truss, and we'd have the support reactions that we would use in our free body diagram. So we don't want to treat those support reactions as unknowns after we make our cut. We want to do that before. So we make a cut and we draw a free body diagram of whichever side is simpler. We'll have 2 sides of the truss, and one section or one side of the truss could be a simpler free body diagram, fewer unknowns, or fewer forces, not unknowns, but fewer forces. So we want to just deal with whichever side is simpler. So that's it. We cut based on the desired members. If we have to get the support reactions, we get those before we cut, and then we draw a free body diagram. After we make the cut, we draw a free body diagram of whichever of the 2 sides is simpler. A couple tips. When we do our equations of equilibrium, we want to sum the moments about the intersection point of 2 lines. So here is our free body diagram for the left section of the truss, and whenever we apply the equations of equilibrium, we could take the sum of the moments about point G, and by doing that we would have only one unknown in that equation, and that would be FBC, because FGC and FGF both intersect point G, so they wouldn't appear. So that's one tip. We want to take the moment about the intersection point of 2 unknowns. And then another tip, whenever we have 2 parallel forces, we start off with the sum of the forces in the perpendicular direction. So here for this example we have FGF and FBC are parallel, or not parallel, they're anti-parallel, but they have no y components. So before we take the sum of the forces in the x direction, we want to take the sum of the forces in the y direction and set that equal to 0, because that will have only the unknown FGC in that equation. So those are the two tips for working these just to make them faster, and doing that allows you to solve directly for an unknown, meaning there will only be one unknown in one equation. On to a couple of example problems. Fundamental problem 6-7. This problem asks for force in members BC, CF, and FE. So we'll go ahead and write a little table here. BC. Oh, I didn't want to use FBC, FCF, and the force in member FE, so FEF. So those are the ones we want to solve for. BC, CF, and EF. So just sketching real quick this truss here. We will want to take our section right through here. That will turn the internal forces in those three members into external forces. And we've got, oh, and for the problem, okay, so we would have the reactions over here. We've also got external forces. So there's the free body diagram of the truss. And just looking at that, it will be simpler to consider the section of the truss on the right. So here is our free body diagram for the method of sections. So there is the section of the truss we're working with, and I'm showing points C, D, and E, joints C, D, and E, and then the cutting line cut through these members. And so I'll go ahead and draw them all in tension. So this is FBC, FCF, and FEF at the top. And that is a 45-degree angle. So there's our free body diagram for this section of the truss. And now we can apply the equations of equilibrium. Oh, it's not a completed free body diagram. I neglected the external loading. So there's 600 pounds at joint C and 800 pounds at joint D. Okay, now we have the free body diagram. And we can apply the equations of equilibrium to find the forces in members, BC, CF, and EF. We'll go ahead and start with some of the moments about point C. FEF will provide a positive moment, and its moment arm is 4 feet. So we have 4 times FEF, and then minus 800 times 4. And those add up to 0. So FEF is equal to 800 pounds. And that is in tension. Move on now to forces in the y direction. The only unknown in this equation will be FCF, and that is at a 45-degree angle. So the y component of FCF is square root of 2 over 2 times its magnitude. And all those forces add up to 0. So FCF is equal to 1400 square root of 2. which is 1979.9. And our final equation will give us FBC. So we have negative 1979.9, and then times the cosine of 45, square root of 2 over 2. Then we have minus FBC and minus FEF, and those all sum to 0. Oh, FEF is 800, so let me go ahead and 800, so that's FEF, and those add up to 0. So it looks like FBC is drawn in the wrong direction. So what we come up with is that FBC is negative 2200. And so it's drawn improperly. It should be drawn in compression. So here's our list of member forces. So it's really a matter of just picking the right line to cut the truss at, and then drawing an accurate free body diagram of the section of the truss we want to work with. So that's the free body diagram, and then it's just the equations of equilibrium, which we've got lots of experience working with. And those three equations, because these are planar trusses, so we only have three equations, those three equations will give us our three, at most three member forces. So we got FEF is in tension, FCF is in tension, and FBC is in compression. And it's in compression, we know, because we drew it in tension, but then we came up with a negative number. So it should actually be pointing the opposite direction. Here now is another example, and this is fundamental problem 6-9. So, in this problem, we want to get forces in members JK, DK, and CD. So that will be JK, DK, and CD. So we'll want to draw a line right through here, and that will be our imaginary line or imaginary cut. And so we will then work with either the left section or the right section, whichever we feel like. And in those sections we'll have these reactions. So we need to get reactions before we make the cut. If we think we'll end up working with the left section, then we need to get the reactions at A. If we think we're going to end up working with the right sections, then we'll get the reactions at G. I'll go ahead and say we're going to work with the right section, so we'll get the reactions at G. So here's the free body diagram of the entire truss, which we're drawing in order to get the reaction at G. So here's FAY, FAX, and then the applied loads, okay. So the only equation we need here is the sum of the moments about point A. And so we have negative 20 times 2, negative 30 times 4, negative 40 times 6, and then FG times 12. And those add up to 0 because the truss is in equilibrium. So that gives us that Fg is equal to 33 1/3 kilonewtons. One other thing we need to do for the problem, well, we'll deal with this in a second. So now we'll go ahead and make our cut, and it's going to be, right about here, between K and J, going down. So I'll draw the rigid body for this section of the truss. Okay, so here we have point J, and here's D, and here's G. And I just left off all the other members. We're considering this as a rigid body, and we don't care about those internal forces, so I'm not going to bother the other members, bother drawing the other members. All right. So we've got FD, or whatever, not FD, but the 40 kilonewton applied load, FG, 33 1/3, and then we have these unknown forces. FJK, FDK, and FCD. We need to figure out this angle phi here. It's shown more clearly in the figure on the right, this angle phi, so that we can get the x and y components of force in member dk. And yeah, so here's the free body diagram. We just need to figure out phi because that's not known yet. So phi is the inverse tangent of 3/2. So and that is 56.301 degrees. So now we can take the sum of the forces in the y direction. That will have only one unknown in that equation, so we can solve directly for FDK. So we have FDK sine of 56.301 minus 40 plus 33.3 repeating, and that adds up to 0. So that's the force balance on this section of the truss. And that equation gives us that FDK is equal to 8.0123 kilonewtons. And it's in tension. Now we can use the sum of the moments, and we want to take the moments about a point where two of these forces intersect, so we'll do point D. And so we have FJK, and it has a moment arm of 3, and it's a positive moment, so 3 FJK. And then FG provides another positive moment, so that's 6 times 33.3, and that adds up to 0. Those are all the forces that generate moments about point D. This gives us that FJK is equal to negative 66.6, repeating, kilonewtons. Okay. So it's good to have a little table up here for the answers when we start dealing with these negative numbers and everything. Okay. And this will be our final answer. And hopefully you'll see why in a second, why it's nice to have this table. So FDK is 8.01, and that's in tension. FJK is 66.6, and we drew it in tension, but it's a negative number is what we came up with, so it must be in compression. So it's, and then now that we have that written down, this will be where we'll refer to our value for FJK. because our next equation is going to be the force balance in the x direction, so we'll revisit FJK. And we could stick with this drawing and use a negative number, but what I'd prefer to do is change the drawing, so FJK, show it in compression, and then we'll use this number. So that's why it's nice to have a little table with the final answers when working these problems. Okay, so now we'll do the force balance in the x direction, and we have FJK, negative FCD, negative FDK cosine of phi, and all those add up to 0. So that gives us that FCD is equal to 66.6 repeating minus 8.01223 times cosine of 56, which is 62.2 repeating. So FCD is 62.2, and it's in tension because our positive number here agrees with the figure. So we use the method of sections to find the forces in the three members DK, JK, and CD. And 2 are in tension, 1 is in compression. So for this problem, we needed to find the support reaction either at A or G, because after we make our cut, both resulting sections are going to have support reactions in it. So we went ahead and found the reactions at G as a first step, and then drew the free body diagram of the section of the truss and applied the equations of equilibrium for these 3 unknown forces. And that is how to use the method of sections to find forces in a truss. And the method of sections is useful whenever you want to just find the forces in a few members. So you can just make your cut through those members that you're interested in.